All right, class. So now that we have talked a little bit about LRFD design, let's do an example really quickly so you get an idea of the process. Here we have a fairly simple design where we have a round rod coming in and being pinned here at this connection. So let's dive into this. Now I've taken the liberty of sketching this out for us and categorizing all the important information. We've taken a section at A, we take that cross section, we see something that looks like this. Clearly there's a hole in the middle, that's representing where this pin goes through there. I probably should draw this a little bit. Let's scoot this section AA probably closer to this. Put our pin right there, make a small modification, then I'll make a little bit more sense. And this pin is fairly large. It's not to scale. So we've got a large hole here in the middle for our pin. So we could see failure at AA, or we could have a failure at our section here. Let's take a look at both of those cases and see where we see that failure. We're given, in this case, instead of allowable stress design, we're given our load factor, this is phi, and our resistance factor and our load factor, gamma. So let's figure out first, we want to make sure that figure out what our Pmax is. So that's our final goal. So we need to check both of those sections. So what I like to do is make an assumption. Let's say, does it fail at AA or does it fail at our rod? That's our first question. Now, we could directly compare force, right, to figure out which one fails first. We could also compare stress. That's probably a better way to do it since they're both in tension. Now, in this particular case, because we're looking at this in terms of P, whether we look at it in stress or force, it doesn't really matter as much. So let's use stress. And the one thing that's going to control stress the most is area. So let's compare area in this case. By figuring out which one has the smallest area, we find the critical section. So the critical section, in this case, because they're both in tension and they're going to be using the same factors, right? We have the same stress, we have the same resistance factor, and we have the same load factor. Critical section is going to be based on area. The smallest section is going to fail, which is pretty intuitive if you think about it. So let's compare areas. So the first area, let's calculate it here, is the area of a rod. We'll call that A rod. And we're going to say it's going to look like pi divided by 4 times our diameter squared. In this particular case, we're talking about pi times our diameter of 40 squared divided by 4. And then let's also get our area for our section AA. Now I could do a bunch of work and take this out of here, but my effective height, if I look at both of these sections, if this total height is 120 and I'm taking out a 60 millimeter hole, I can say the effective height is 60 millimeters and my width, this whole thing is 50 millimeters. So my total area is 3,000 square millimeters for that one. And let's calculate at our rod. So we got pi over 4 times 40 squared. That's going to be 1257 square millimeters. Based on this, it's very clearly that the A in this particular case, our area of our rod is critical. And that's pretty interesting. This is kind of an interesting connection that we're going to see a whole lot. This is one of the few times where I'm going to see this fail at the rod instead of at a connection. But now that we know that that's our critical dimension, we can use that to figure out what our stress is. All right, so we want to figure out what our expected load is. So we say, okay, we want to check that phi times P of n is greater than or equal to our load times its load factor. So our load factor is given there, that's our gamma, and we're just going to call this P, right? We want to make sure that this is our capacity versus that, and that this is greater. Now, if this is at failure, or the greatest P that we could see is when these two are equal. So to figure out what P max is, we can just rearrange this a little bit and say P max is equal to phi times Pn divided by our gamma, right? And that would be in terms of force. And what we have is stress. So if we want to figure out this in terms of stress, we're going to convert that P of n using our yielding stress. P of n, well, P of n is going to be our yielding stress times our area, right? Rearranging that. Stress is Pn divided by area. So I can plug in what I know. I can say this looks like, I'm sorry, I should say sigma y. Sigma y, stress. So I can plug that in. I can say, okay, that looks like phi times sigma y times area divided by our load factor, gamma. Our load factor, gamma, is 1.4. Our resistance factor, phi, is 0.9. Our stress is 250 megapascals. And our area in this particular case, we want to use our critical area, is that 1257 square millimeters. Now, we got to be careful here, make sure our units match up. In this particular case, I've got megapascals, that's 10 to the 6 newtons. In this particular case, our millimeter squared, remember that this is 10 to the negative 6, because it's 1,000 divided by 1,000, so 10 to the negative 6. So those units actually cancel out. And what we find out is that this is going to give us an answer that's just going to be in newtons. So that makes things a little bit easier. And if I bust out my calculator and I do 0.9 times 250 times that number that I calculated before, 1257, divided by 1.4, that's going to give me a pretty large number here. I can plug that in here. That number that we find is going to be, write it over here, is 202,018 newtons. And in engineering, right, we're always going to go to 3 sig figs. I'm going to say that this is just 202 kilonewtons. That's where we want to stay. And that's how we solve this particular one. So let's go over those steps really quickly. First, we figure out what our critical area is. In this particular case, because we have the same type of failure, tension failure, or how do we know it's tension? Because this is a average normal stress. We have a tension failure because it's positive. Because it's a tension failure, we just have to compare areas in this case. Sometimes we might have to figure out what this is numerically, but in this particular case, we can just compare areas. By comparing areas, we find that our rod is the critical part because it's a smaller area. Once we have that area, we can go back and calculate it, compare it, our capacity versus our demand. We always want to make sure that our capacity is greater than our demand. So if we're at failure, these things are going to be equal. We can rearrange and say, okay, what is Pmax going to be? If we know what Pmax is, we can figure out what Pn is going to be based on our calculation of stress. And our capacity is going to be based on yielding. So we just say, hey, Pn is yielding stress times area. Plugging that in, we can then calculate what our Pmax is for this particular, for these two cross sections.